Hello, and welcome to The Space Above Us. Episode 114, Space Shuttle Flight 43, STS-48, Science in the Stratosphere. Last time, we talked about the extended flight of STS-43. The primary mission was to deploy TDRS-E, which was successfully accomplished just a few hours after launch, but the crew had a whole bunch of side experiments to work on during the 9-day mission. As Atlantis and its crew readapted to life in 1G, Discovery was back on the pad and ready to usher in a new era of Earth science. I'm about to gloss over a whole bunch of history, science, and policy, but we've got a space mission to get to, so I want to keep things brief. Back in the 1970s, the world had a problem. It seemed that a class of chemicals that were commonly used in consumer and industrial products were damaging the Earth's atmosphere. Chlorofluorocarbons, or CFCs, were useful as refrigerants, as propellants for aerosol products, forcing stuff like hairspray out of a can, and a number of other applications. The stuff was apparently great, but it came at a cost. It was eating away the planet's ozone layer. Ozone is a molecule consisting of 3 oxygen atoms, instead of the usual 2 that we're accustomed to breathing. The ozone layer is basically just what it sounds like, a layer of these ozone molecules enveloping the planet. This is important because one thing ozone is great at is absorbing high-energy ultraviolet light from the sun. This UV light is dangerous to crops and animals, including humans, so the ozone layer is really helping out. But this protective layer is not necessarily a permanent feature. High in the upper atmosphere, there is a delicate chemical dance going on. As ozone absorbs UV, it breaks down. I'm not a chemist, so please take this with a grain of salt, but I believe what happens is the O3, ozone, breaks down into O2, normal oxygen molecules, and lone oxygen atoms. This is the atomic oxygen that we've mentioned before, which is extremely reactive and can be damaging to spacecraft in low Earth orbit. The atomic oxygen can now find new O2 molecules to glom onto and recreate more ozone, and balance is thus restored. That is, until CFCs entered the picture. CFCs released in the lower part of the atmosphere were suspected to be making their way into the upper atmosphere, where they too were broken down by UV light. The chloro and fluoro of chlorofluorocarbons stands for chlorine and fluorine, and those of you who are chemists will know that those are some extremely reactive elements. So now, instead of atomic oxygen recombining with molecular oxygen and preventing us all from getting skin cancer, it's combining with these reactive CFC-related compounds. So we were getting a whole bunch of these CFC byproducts and not much ozone. The upshot of this was that the ozone layer was gradually being depleted. Faced with this clear environmental change, world governments got to work on trying to gather more data in order to make informed policy decisions, which is, refreshing. Scientists fanned out across the world with an array of instruments, airplanes, balloons, and so on to study the ozone layer and how it was changing. This was all great, but what they really needed was something that could pull all their data together, something that could make observations around the clock, something with a global perspective. They needed a satellite. Enter the Upper Atmosphere Research Satellite, or UARS, the first satellite in the Mission to Planet Earth program. UARS had a tricky job of studying the upper atmosphere and how it interacted with the lower atmosphere. I say this is tricky because, well, let's take one quick step back. Scientists break the atmosphere down into multiple layers. The layer that you're most familiar with is the troposphere. It goes from the ground up to around 15 or 20 kilometers. Incidentally, I once saw a toy rocket that proudly proclaimed on the box that it would launch into the troposphere, and I was not impressed. But don't let me get distracted. As you move up in the troposphere, the temperature gets lower and lower, until it doesn't. We've reached the stratosphere. Here, the air is thinner, and the dynamics are different, such that things start to get warmer again. This is largely due to the ozone layer, which hangs out in the stratosphere, absorbing UV light, and as it absorbs that light, it gets hotter. If you keep going up, though, this effect eventually tails off and it starts getting colder again. This is the mesosphere, up around 50 kilometers. Keep going and things change again at the 80-kilometer mark, the thermosphere. At this point, we're essentially in space, and that brings me back to my point of UARS having a tricky task. One of UARS's jobs would be to gather data on the mesosphere. It's too high for balloons and too low for satellites to fly through, so the mesosphere is not easy to study. So, UARS was packed with all sorts of cutting-edge remote sensing equipment that would allow it to study the upper atmosphere, even from space. Some instruments would study the composition of the atmosphere at 20 different altitude levels. Some would study the horizontal mixing of gases in the atmosphere. Some would study the energy being pumped into the overall system. And all of them would work together to better understand just what was going on in, well, the air above us. Let's meet the crew that had the job of delivering this critical environmental spacecraft to orbit. Commanding STS-48 was someone who we've seen twice now, J.O. Creighton. Most recently, we ran into Creighton when STS-36 had to be rescheduled, at least in part due to him having a cold. Though I guess we can't hold that against him. After a little rest, the commander was good to go, and STS-36 successfully deployed something mysterious for the Department of Defense. With this flight, he marks his third and final mission. Joining Creighton up front was our pilot for today, Ken Reitler. Kenneth Reitler was born on March 24, 1951 in Patuxent River, Maryland, though considers Virginia Beach, Virginia to be his hometown. Reitler attended the U.S. Naval Academy, earning a bachelor's in aerospace engineering, which he would eventually supplement with a master's in aeronautical engineering and a master's in systems management. He became a naval aviator, learning how to fly, and being deployed to Florida, Iceland, and Sicily, which is quite a range of climates. He then went to the Navy Test Pilot School, which also happened to be in his birth town of Patuxent River, Maryland, and became a test pilot. He flew the P-3, S-3, T-39, T-2, OV-1, and TA-7, and served as an instructor. Well, soon he can add OV-103 to the list, because he was selected as an astronaut in June of 1987, and this is his first of 2 flights. Continuing back in the flight deck, we find Mission Specialist 1, Sam Gamar. We last saw him flying as Mission Specialist 3 on the classified flight of STS-38, deploying something that maybe prowled its way into geostationary orbit. I'm still wondering why his nickname is Sam if his actual name is Charles, but maybe I'll find out next time since this is his second of 3 flights. Sitting right in the center of the flight deck was Mission Specialist 2, Jim Buckley. As Mission Specialist 2, he was also serving as flight engineer, which is a role that I have criminally neglected during the shuttle program. But basically, the flight engineer served as a third pair of eyes to help the pilot crew during ascent and entry. They watch what's going on and help out with the checklist. It makes sense that Buckley was serving in this role, since this is his 4th flight, making him only the second person to fly 4 times on the shuttle, the first being our old friend Bob Crippen. 4 flights is a pretty good run, though, and Buckley decided to move on, making this his final mission. And rounding out the crew, Mission Specialist 3, Mark Brown. We last saw Brown flying on STS-28, another classified mission, which maybe deployed SDS-2. I'm sure Brown was glad to get this unclassified mission, since he'd have something to talk about after retiring from NASA. This is his second and final flight. This seems to be just a coincidence, but I thought I'd mention that, I also noticed that almost everyone on this flight has recently flown on classified DoD missions deploying secret stuff. And while Jim Buckley's previous flight was the nice and unclassified deploy of TDRS-D, his first flight was on STS-51C, which was another secretive mission. Interesting. I'd bet that this Earth observation flight was a nice change of pace. You may have also noticed that out of a crew of 5, there's only 1 rookie on this flight. I would guess that this is no accident, since the STS-48 crew would have an unusually short training period before their flight. UARS had a nominal mission duration of only around 20 months, and it was important that it had a chance to observe 2 full winters in the Northern Hemisphere, which meant that it needed to get off the ground in the fall or wait a whole additional year. With the usual shuttle program inertia pushing the schedule forward and UARS requirements pushing the schedule back, what got squeezed was the time for the crew to prepare. So it makes sense to pick a crew who was already up to speed on this whole spaceflight thing. The need to get UARS into orbit quickly made this mission a rarity in the shuttle program. Its launch was moved earlier. Incidentally, this also explains why we jumped right from STS-43 to STS-48. The launch was eventually moved back 9 days, which just so happened to be the earliest launch date that allowed the crew to complete their training. So it was that on September 12th, 1991, the crew found themselves strapped into their seats in Discovery's crew cabin, working through the final parts of the pre-launch checklist and preparing for the ride uphill. The liftoff was delayed by 14 minutes due to poor audio quality when communicating with the crew, but this was determined to be an issue with ground equipment and the countdown was continued. So with -9 days of delays, no scrubs, and only a minor issue during the countdown, Discovery leapt off of the pad at 7:11 p.m. Eastern Time. STS-48 was underway. Before the mission lifted off, pilot Ken Reitler had been concerned about his ability to reach various switches and dials in his bulky pressure suit as the G-forces mounted. With that in mind, soon after the flight started, he began reaching out to various places around the cockpit just to get a feel for things. As he did this, Mission Commander Creighton kept glancing over at him before finally saying, "Would you knock that off?" Rule number 1 of flying on a shuttle mission: don't distract the commander during ascent. Discovery's destination for today's mission was an unusually lofty one, a roughly 570-kilometer orbit. This already makes the flight noteworthy for being one of the highest missions of the entire program, but the orbit also had a high inclination for the shuttle, 57 degrees. So while this flight does not break the record for highest shuttle altitude or inclination, the combination of nearly breaking both is pretty neat. UARS would be deployed by the Remote Manipulator System, which means the rhythm of this mission is a little bit different than the IUS-based deploy of TDRS from the previous mission. With an RMS deploy, the spacecraft can extend its appendages while still grappled, and the crew can hop outside in case there's any issue, just like they did with the Compton Gamma Ray Observatory. But, as we learned, EVAs were not to be scheduled early in the flight, so we have to wait until Flight Day 3 to see UARS spread its wings. So, let's take a look at some of the other stuff on this mission. Flying on Discovery was a first for spaceflight: a digital camera. This is actually sort of a fuzzy line, since there's obviously been digital sensors on stuff like the Hubble Space Telescope and on reconnaissance satellites, but what I mean is that this was a normal handheld camera that was operated by the astronauts and actually looks like a camera. Basically a DSLR. Sort of. Consumer-level digital cameras didn't really exist yet, so this was a modified Nikon F4 camera body fitted with a charge-coupled device sensor where the film would normally go. The sensor could only take photos 1024 pixels on a side, and instead of color it had 256 shades of gray, but it could do something that no film camera could do: downlink images while the mission was still underway. The mission press kit speculated that the presence of digital cameras on future space missions, especially lengthy space station flights, would be increasingly important, and I've got to say they got it pretty right. Alright, Flight Day 3, Deploy Day. Mission Specialist Mark Brown hopped onto the RMS controls and made sure everything was working alright, then latched onto the grapple fixture on UARS. Brown raised it out of the payload bay and began to slowly spin it around so that the high-gain antenna was facing in the right direction. The RMS is pretty slow though, so this will take a while. While UARS gets into position, let's learn a little bit about its instruments. UARS had 10 instruments on board, which were all supporting the same overall experiment. Well, actually the active cavity radiometer irradiance monitor was just sort of hitching a ride so that it could keep an eye on the sun, but the other 9 were all working together in service of the same mission. Broadly speaking, they could be broken down into 3 categories: chemistry, dynamics, and energy inputs. If scientists could understand these 3 categories in the context of the upper atmosphere, they could answer a lot of questions. Let's take a quick look at each category. First, chemistry. This category contained 4 experiments: the cryogenic limb array etalon spectrometer, the improved stratospheric and mesospheric sounder, the microwave limb sounder, and the halogen occultation experiment. That's a lot of crazy jargon, but in short, these 4 experiments used sophisticated instruments to study the chemical composition of the upper atmosphere. Where was the ozone? Where were the chlorine compounds that resulted from CFCs breaking down ozone? Where was the water vapor, the methane, nitrogen, and other various gases? The data coming from these instruments would give scientists an idea of what was up there, where it was, in what concentrations, and how it was changing over time. Next, dynamics. This category contained the high-resolution Doppler imager and the wind imaging interferometer. These 2 instruments were responsible for measuring the movement of air and wind in the upper troposphere, the stratosphere, and the mesosphere. Understanding the motion of air and the dynamics of wind would help scientists better understand how all the chemicals they just learned about were moved around and mixed together. Just one concrete example of this it had been suspected that CFCs from the northern hemisphere were migrating down to the southern hemisphere, where they were punching a hole in the ozone layer. UARS was able to confirm this. Lastly, energy inputs. The ozone layer depends on a delicate balance of UV energy being absorbed and breaking down molecules, along with the upper atmosphere chemistry rebuilding it. So it was crucial to understand what energy was being pumped into this system. The three instruments comprising this category were the Solar Ultraviolet Spectral Irradiance Monitor, the Solar Stellar Irradiance Comparison Experiment, and the Particle Environment Monitor. Combine all three of these categories, along with a reasonably high orbital inclination, which allowed UARS to monitor up to 80 degrees in latitude, and the spacecraft was able to build a complete picture of what was happening in the upper atmosphere all the way across the globe. It looks like Brown and the RMS have turned UARS around and they're ready to go. The Goddard Space Flight Center, operators of UARS, issued the commands to begin deploying its appendages. The 9 by 3 meter solar array deployed with no issues, as did the high-gain antenna with its 1.2 meter diameter dish. So no contingency spacewalk for Gamar and Buckley. There was one minor hiccup when the primary transponder was unable to communicate with TDRS, but that's what backup transponders are for. After delaying a bit to try to get the primary working, Goddard decided that they were fine with deploying while on the backup. So, 2 days, 5 hours, and 12 minutes after lifting off from Florida, the Upper Atmosphere Research Satellite was released and free to begin its mission. After a further day in lower orbit spent on fixing the transponder issue, UARS raised its orbit a further 30 kilometers to its operational altitude of 600 kilometers. We'll leave UARS to putt-putt its way to operational orbit and turn our attention back inside the orbiter, specifically down on the middeck. One thread we've seen running through many of these missions is preparing for a future space station. We've seen extended stays in orbit to study the impact of microgravity on the human body. We've seen heat pipe technology, EVA techniques for building and moving around large structures, and even testing the best way to move the mouse arrow around a computer screen when your mouse keeps floating away. Well, today we'll be adding another experiment to the list, the Middeck Zero Gravity Dynamics Experiment, or MODE. I think using the zero as an O is sort of cheating, but I guess we'll take it. Especially since it's 1991, the year that the World Wide Web became public. So the folks who named the experiment were clearly just getting into the spirit of LEET speak. Like many of the experiments I just mentioned, MODE was focused on gathering some basic data on how things behave in space, as well as validating computer models and ground simulations. One thing that any future space station was very likely to have was long trusses. Skylab didn't have any need for stuff like that, but Skylab also had a Saturn V tossing the whole thing into orbit in one big lump. Space Station Freedom would instead be assembled piecewise by a series of space shuttles, so structural trusses made a lot of sense. Given that, it was important to understand how the trusses behaved. How do they flex? How do they bend? What happens when you apply forces to them or make them vibrate? Sure, you could just make it so rigid that you don't have to think about it, but then you've over-engineered your truss so much that it's too heavy to carry on the shuttle. So, in an effort to better understand the dynamics of these truss structures, the crew got to work having a little fun, essentially assembling Tinker Toys down on the middeck. The trusses were small compared to a space station, but pretty big for the middeck, stretching to just under 2 meters. Once assembled, specialized equipment would vibrate the trusses in specific ways while sensors and video cameras noted the results. The MODE experiment was also evaluating rotary joints that were being considered for use on the solar arrays, so the crew tested the truss and rotary joint set in different configurations. MODE also included a study of the behavior of fluid propellants in space. For this, fluids were placed in clear containers that would elicit different behaviors, and then the crew would observe the results. Rather than using real propellants, which can be pretty dangerous, they used some fluids that behaved similarly. 2 containers had water, and 2 had silicon oil. Neat. The experiment went smoothly, and engineers could cross out one more thing on their long list of unknowns when planning a space station. Alright, while the crew plays with their toys, let's take a quick look at what UARS was able to accomplish over its lengthy lifespan. UARS was only planned to have a 20-month-long mission, partially because that's how long the cryogenic supply for the Cryogenic Limb Array Etalon Spectrometer would last. I'm not sure why this was the case, but CLASS, I'm not saying that whole thing again, used a solid block of carbon dioxide and a solid block of neon for its cryogenic supply, which is pretty interesting. Despite the limited life of class, it was hoped that UARS might provide useful data with its other instruments for as long as 8 to 9 years. So the team would have been delighted to learn that in fact it lasted 14 years, over 8 times the original goal. In fact, when the mission finally did end, it was for budgetary, not technical reasons. Over those 14 years, UARS confirmed the hypothesis that CFCs released in the northern hemisphere were migrating to the southern hemisphere and contributing to the hole in the ozone layer over Antarctica. And it was able to track the status of that hole as it slowly recovered due to the banning of CFCs. UARS was also on hand to study stuff that nobody could have predicted. Just a few months before Discovery launched, Mount Pinatubo in the Philippines erupted. The volcanic eruption was catastrophic for the Philippines, but the entire planet was affected by the massive amounts of ash and gas suddenly pushed into the atmosphere. With UARS and its specialized suite of instruments on hand, scientists were able to track the spread of these gases and watch when they ate away at the ozone layer over the equator. Unlike harmful human activity, however, the volcano eventually stopped, so the ozone over the equator was able to recover. Between its contribution to the understanding of the ozone crisis, expanding our knowledge of the mesosphere, and providing a much-needed global snapshot of the dynamics of the upper atmosphere, there's no denying that UARS was a success. And just as a cherry on top, the effort to build and launch UARS came in almost 5% under budget. Not many space projects can claim that. All good things must come to an end, however. So, in the mid-2000s, with new satellites flying and budgetary pressure is always a concern, NASA decided to shut down UARS and expedite its reentry. Actually, in the same decision, they also ended another mission we know pretty well, the Earth Radiation Budget Satellite, or ERBS, which was launched on STS-41G, but one mission at a time. The option of using the shuttle to recover UARS was examined. It's always helpful to study stuff that's been exposed to space for a long time, and it would remove any risk posed by an uncontrolled entry. Plus, maybe they could put it in a museum somewhere, who knows? It was technically feasible, but it wasn't worth the extra expense, the time slot on the shuttle's schedule, or the risk to the astronauts. So no ride home for UARS. Crashing a satellite into a specific swath of ocean is actually pretty tricky to pull off, and requires a fair amount of fuel. Fuel that UARS did not have. So it would not be able to perform a controlled entry. But Goddard operators could at least hasten its return and try to make life easier for other satellites. Just one less piece of space debris to worry about. Plus, best practices called for passivating the spacecraft, including venting any remaining fuel. And the only way UARS could vent fuel was to burn it in the thrusters, so we may as well lower the orbit. A detailed plan was worked up on how to passivate the spacecraft and prepare it for entry, and on August 5th, 2005, the majority of the instruments that were still functioning were shut down. On August 21st, one of the batteries began to fail, which triggered the backup emergency end-of-life mission plan. As sad as it was to end the mission, it would have been much worse to miss that safe ending by a few weeks due to a bad battery. After a series of maneuvers, UARS had lowered its orbit and emptied its tanks. On December 14, 2005 at 17:16 UTC, the Upper Atmosphere Research Satellite was shut down. Its orbit had been lowered to 518 by 381 kilometers, and it was expected to re-enter within 4 or 5 years. Over the next few years, atmospheric drag inexorably pulled it lower and lower in its orbit, and on September 24, 2011, just a few months after the shuttle itself had been retired, UARS streaked through the region of the atmosphere whose secrets it had unlocked and harmlessly splashed down in the Pacific Ocean. Meanwhile, back in 1991, STS-48 is still chugging along. I mentioned how one reason to deorbit UARS was to reduce the amount of debris in orbit. This is a growing problem today with the large number of functioning and non-functioning satellites flying around, but in the early 1990s it was not yet a big concern. So it was pretty unusual when on Flight Day 4, Discovery had to execute a 7-second retrograde burn using its RCS thrusters. The burn slowed Discovery down by about 0.6 of a meter per second, lowering its orbit by just over a kilometer. Why do the burn? Because without it, Discovery would have whizzed within 1.2 kilometers of a defunct upper rocket stage, which had delivered a Soviet electronics intelligence satellite to orbit back in 1977. The collision avoidance maneuver was a first for the shuttle, but it would not be the last. In fact, one last little postscript on that topic, UARS itself caused a mild headache for the International Space Station back in October of 2010. Their paths were becoming just a little too close for comfort, so the ISS made a small adjustment to steer clear of the old environmental spacecraft. There were no extended operations for this mission, so on Flight Day 5 it was already time to come home. The mission was planned to be the first night landing at the Kennedy Space Center, but rain and clouds in Florida dictated that instead, Discovery and its crew would do one more lap around the world and then land at Edwards in California. The scale of spaceflight, even in low Earth orbit, still somehow catches me off guard. The reentry burn was performed as Discovery passed between South Africa and Antarctica. It then flew over Tokyo and then Alaska, crossed into Oregon flying at Mach 11, 58 kilometers up, in the mesosphere as we now know, before safely touching down at Edwards in California just 70 minutes after firing its engines. Discovery rolled to a stop, and all 5 days, 8 hours, 28 minutes, and 27 seconds of STS-48 were in the books. Next time, we have one of the last remaining shuttle missions flying for the Department of Defense. Don't worry though, it's unclassified, and we can take a look at all the pictures of the payload bay that we want. Plus, Atlantis chalks up one final dusty landing for the shuttle program. Ad Astra, catch you on the next pass.